Hi again, AP Statistics students, and thanks for tuning in. Uh, we've finished up chapters 1 through 4 now. Remember, we did 4 to begin with, so we're going to go into chapter 5 now, which is a bit of a departure because in chapter 5 we really start looking at some of the more theoretical aspects of probability, and it's not so much grounded in data. I mean, there's always going to be a data component to statistics, but there's going to be some theoretical things that happen in this one that make it a bit of a departure, like I said, from what we're used to seeing. And so when we get into this part, this is also the part of the year where we start to examine a lot of different games of chance. And so I think I mentioned earlier to you that we will be looking at some of the various games you might find in, say, a casino. We'll be looking at some lottery-based games, and just in general, looking at it, how do those games work specifically, and then more generally speaking, why are they profitable for the people that are running those games? And so we'll take a look at some of the probability, and then again some of the reasons why perhaps that's not the smartest thing in the world to do with your money. So we will be taking a look at some of that stuff later as well. To begin with, though, we have to get some of the basic understandings of probability, some of the language of probability. We have to get that figured out. And so we'll start off in section 5.1 with some pretty basic definitions. We want to first of all talk about what do we even mean by probability. And to do that, we're going to talk about randomness. We're going to define probability. I'm actually going to define it in a couple of ways. And we'll talk about something called the law of large numbers, which you can see on the screen now. And then finally, we'll finish up with this idea of what do we mean when we say simulation. So let's just dive right in. In probability theory, we're going to work on the assumption that that the events that we're looking at, that the outcomes from the events, they happen at random. And so that there is an element to randomness to all of the events that we're talking about. And so whether it be flipping a coin, rolling a die, spinning a spinner, pulling a name out of a hat, the idea is that these things happen at random. Now, that's not to say that there's not a preference or a bias in there, because there could be weighted dice, for example. We could have more of one particular color of ball in an urn than another. So I'm not saying that they take on the events don't happen with an even probability across the board, just that they do so randomly. So that leads us then, once we understand that, okay, we're talking about random events, then what do we mean when we talk about probability? And I've given you two different definitions here. One is from our textbook. So number one says, when you look in there on page 285, you would see the definition that Dr. Starnes gives you is probability is a number between 0 and 1 that describes the proportion of times the outcome, okay, whatever our outcome is, would occur in a very long series of repetitions. So, I'll just do a simple one, like flipping a coin. Okay, the probability that I flip a coin and it lands heads, it's 50%. Okay, or 0.5. Okay, but that does not mean that that's exactly 50% every time. And what this this definition of probability is trying to say is like it's 50% only if we do a very long string of repetitions. Is it possible to flip a coin 10 times and not get 5 heads and 5 tails? Yeah, it is. In fact, I'd say it's probably more likely that you don't get 5 heads and 5 tails. I mean, well, that might be the most likely single event, but it's probably more likely that you would get any other either 4 or a 6 or a 3 and a 7, something in there would probably be more likely than just exactly 5 and 5. So that is one way to think about probability. The other way to think about it, and this is probably the way that if you were in, 7th or 6th grade math, or whenever you first started thinking about probability, it's probably the way they described it, which is the number of chances of success divided by the total number of outcomes. So, I'd say the probability of an event is, number of chances of success divided by the total number of outcomes. And that's probably the one we're most used to seeing. Okay. And what I like to think of this one, this one is sort of a probability you could figure out before you do any data collecting. Okay. If you could figure out the number of chances of success out of the total number of outcomes before you start, then you have a pretty good idea of what the probability of success is going to be in that scenario. How do we know that flipping a coin comes up heads 50% of the time? Well, there's only 2 outcomes and one of them is heads. So 1 success divided by 2 outcomes gives you 50%. So, this idea down here this is a theoretical or a before the fact, before you gather any data, you could figure this out, maybe. This one up here is after the fact. After you've done the data gathering, then you can look at what is the probability of that event. The first definition is probably one we'll use a lot, just because it won't be as simple as I'm going to flip a coin. For example, if I was going to go to the gym and shoot free throws at the basketball hoop, what's the probability that I make a free throw? Okay, well, the way we usually figure that out, okay, if you said very low, you are correct, because I'm a very terrible basketball player. Okay, I freely admit that basketball is never my sport. All right, so yes, it is very low that I will make the free throw. However, that aside, to actually put a number on it, what we would do is actually gather data on me shooting free throws repeatedly after a very long series of misses, and an occasional one that goes in. We would have an idea of what my probability of making a shot would be. Okay, because we don't really know the number of successes divided by the total number of outcomes ahead of time. Okay, so the 2 different definitions of probability happen at different times in an experiment. And sometimes, we won't be able to do the second one because it's not as simple as, okay, I'm going to roll a 6-sided die and I want the probability of rolling a 2. Well, there's only 1 2 out of 6 sides, so of course it's 1/6. Now, the law of large numbers, okay, is that's the one that it tells us that, okay, these two definitions of probability eventually come together. That after a while, with a very long series of repetitions, you will then have a good idea of what the probability of doing the total number of successes divided by the total number of outcomes is going to be. Okay, so it's sort of like the first definition sort of converges, if you are a calculus student, approaches this single value after many trials. And it's the one that people sometimes get mixed up with the law of averages. And there's a tendency to think that the law of averages means, that a baseball player, for example, a very good professional baseball player, gets a hit about 1/3 of the time. So, and that's a very high average. That would be a 333 average for you baseball fans out there. So if you like baseball statistics, oh boy, they're all over the place. And man, we have all kinds of stats that we can grab from baseball. Just a very simple example though, in baseball, a really good batter, let's say, gets a hit 1 out of 3 times on average. Well, that does not mean that when this player comes to bat and it's the 4th time in the game and they've struck out 3 times in a row, that they are quote unquote due for a hit, that they're gonna get a hit. No, that's not what that means. That 333 average means that over the long term, after a long series of attempts of at-bats, on average, that batter gets a hit about 1 out of every 3 times. Okay, so there's no guarantees here that just because we have a 333 hitter that they come to the plate 4 times, they're gonna get a hit. Okay, there's plenty of evidence to the contrary, that if you have a really good batter, they could come to the plate many times in a row and not get a hit. yet over the long term, still have a really high average. That is until they come to play for the Mariners, where all good batters seem to go to die, because every time we draft a good batter, he has the worst season of his career. As soon as he gets traded away, all of a sudden he has a breakout season. I don't know what it is about the Mariners, but they or hitting in Safeco Field, but I'm sorry, it's not Safeco Field anymore. It's T-Mobile Park. I forgot. I'm going to be always calling it Safeco Field because that's what it's been since it opened. So, all right. So the things that we want to pay careful attention to is that when we talk about probability, which definition are we using? Okay, because this first definition is basically relative frequency, right? That's what this is. I don't know if it's all going to fit. Oh, it did. Okay, good. Okay, is it the relative frequency? Or is it this one where we already know what the outcomes are, and then we can just do this nice little ratio here, keeping in mind, of course, that the law of large numbers is the one that tells you, hey, it's 50% of the time it's going to land heads up, but that's only over the long haul. Okay, very easily could flip a coin 10 times in a row and not get 50% heads. In fact, you could probably flip a coin 10 times in a row and get heads 0 times. Not very likely. Okay, I grant you that. It's not very likely that would occur, but it is possible. And so for that to have happened, it doesn't mean, oh my gosh, they've cheated in some way. It just means that, well, that particular event was, well, unlikely. Not totally ruled out of being possible. So it's got a probability of 0.000977. So let's say it happens, let's round up, 1 out of every 1,000 times. You could flip a coin 10 times and not see heads a single time. So yeah, so there's a kind of a weird thing there with the law of large numbers. Okay, it's not 10 flips of the coin. It's not even 100 flips of the coin. Okay, if you flip it 100 times, you're not going to get 50 and 50. Okay, or even 1,000 times. No guarantee it'll be 500 and 500, but it should start to get close to that. And what we should see is that number of flips equal out heads and tails over the long term. So that's the idea behind probability. It's the idea behind randomness and the law of large numbers. Randomness is a weird one because our mind sometimes sees patterns as being impossible in a random event. And if I was flipping the coin, and let's say I flipped it 6 times, tails, tails, heads, tails, heads, tails. Possible? Sure. Okay. Same number of tails and heads. Which one is more likely? Okay, well, if it's truly random, they have the same probability. Okay, the fact that one has what we perceive as some sort of randomness to it versus the other one, which appears to have a pattern to it, doesn't mean that anyone is more or less likely. And so that's one of the things that when we start thinking about randomness and probability and events, we have to fight that urge to call that one, the tails, tails, heads, tails, heads, tails versus tails, 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 heads, heads. Oh man, that second one, there's no way. Yeah, actually, the same probability as the first one we drew. The one I like is when you look at lottery numbers, like people, like we have there's a couple different lottery games out there, but there's one where you pick 5 numbers. Well, could those 5 numbers get drawn? Yes, they could. And is that any different than, a completely, 21, 10, 5, 3, 35? You know, there's no difference between the two if they're drawn from the same set of numbers. Okay. People always look at that 1, 2, 3, 4, 5 one and go, what? You know, and it has to do with, because in lottery games, a lot of times the order is not significant, but we have to fight that urge to say, oh, that one's really not possible, or not as likely as the other, just because it doesn't look as random. All right. The last thing for this first section of probability, now that we have some basic ideas of probability down, is the idea of simulation. Oops. Where'd it go? There it is. And simulation is a technique in gathering data that we're going to use when maybe the actual study we want to do isn't really feasible. And so rather than do that study, we're going to randomly, or because it's some sort of random event, but we can't do it over and over again. The example I always use for this is, there's a company out there, and they needed to lay off 10 employees. Okay, so company must lay off. What happened there? Ten employees. And the CEO says, this is really hard for me. I'm just going to put everybody's name in a hat, and I'm going to randomly draw 10 names. Okay, this is not a good way to run your business, by the way. But he randomly chooses 10 names, and he ends up with 5 women and 5 men who he's going to lay off. And the women in the group are going, well, wait a minute. That's not right. If you really did this the way you said you were going to do, which was to randomly do it, this couldn't happen, because the company is actually made up and it only has 25% of the employees are female. Okay, and so what I would suggest at this point is, in class, what we normally do is say, well, gosh, let's investigate this, but we can't go to this company and like randomly fire 10 employees over and over and over again, right? Like, oh, 10 and 10, hand out 10 notices you're fired, and then be like, just kidding, you're fine, come on back. And then randomly hand out 10 new ones. And then like, oh, we're not serious. Yeah, just come on back, and do that over. That wouldn't be feasible. So rather than do that, we could simulate this event, okay, in a lot of different ways. What I have in my classroom is, I have this box, this kind of weird rectangular shaped box, and inside of it I have blue beads and yellow beads, and there's a couple thousand beads in there, and 75% of the beads in the box are blue, 25% are yellow. And so rather than repeatedly fire people from this company, we simulate the firing by using a probability device, a model that accurately represents the proportions in the situation. So yeah, so if we were in class, I would have this box somewhere, and we would be, we would be using the box, and we'd say, okay, and the box has a hole in the side of it, and inside of it there's all these beads. And I always make a joke, there's a bunch of beads and then like one mean spider that lives in there. There's not actually a mean spider in there. So there's a hole in the box, and you reach your hand in, and then you grab, There's all these beads. Okay, but the beads are 25% yellow and 75% blue. And so by reaching in and randomly pulling out 10 beads, okay, we would then be simulating the firing of 10 employees, and we would just count the number of yellow or the number of blue that are in there. And that's a way to do a simulation. Works pretty well. Okay. Another way to do it would be to say, well, how about this? We will randomly draw a number between 0 and 99. That's 100 numbers, right? And if the number is anywhere between 0 and 24, that's a woman that got fired. And if it's from 25 to 99, that's a man that got fired. And we could randomly draw numbers using a calculator, using random.org or whatever. The idea is that the simulation is designed to have the exact same probabilities as described in the problem. And so that is a great technique for when the probability model that you want, or the event that you want, isn't really feasible to do in practice. Okay, because it's, would be mean to repeatedly fire people. And man, if you're the person getting like the same notice every week, like, oh great, there they go again, do another study. Yeah, stuff like that would be bad. So we simulate it. The key is to make sure the probabilities match up. So I think that's everything for section 5.1 today, guys. So thanks so much for coming in and learning about probability today. We've got a whole lot more probability coming up. Lots of different rules for probability, how to analyze different events with probability, and of course, taking a close look at some probability-based games as well. So, all right, guys, thank you so much, and I will see you in class. Bye-bye now.